Thank you, Daniel.
All right, so our next speaker is Jeremy Liu. He is a graduate student in quantum computing.
So the topic I'm talking about today is the dynamic topology reconfiguration of Boltzmann machines on quantum annealers. So to give a quick overview, what we want to do is to fit a data model, in our case, a Boltzmann machine, onto D-Wave's quantum annealer. We want to do this because the annealer potentially allows us to implement a richer connectivity in Boltzmann machines that will give better results than what we can find on a classical machine. Now, the problem is that quantum annealers have limited resources. It has few quantum bits and has few connections between these qubits. So the question becomes, how can we use our limited resources effectively? So one step towards this is to make an observation that the way that we choose to map our Boltzmann machine variables onto the annealer qubits influences our data modeling results. So let's try to make some mapping choices that gives us benefit. So going forward, I'm going to talk quickly about Boltzmann machines, then quantum annealers, what the two have to do with each other, and then our work about trying to use our limited resources effectively. So here, what is a Boltzmann machine exactly? So a Boltzmann machine is a generative data model in which we have visible units that represent data. We have hidden units that are latent factors that control the distribution of this data, and these can be used as building blocks for other neural networks. Furthermore, Boltzmann machines are energy-based. That is, they define a Hamiltonian, which assigns an energy to every possible network configuration, and configurations that have lower energy tend to appear more often when we sample the network. Now, on the right-hand side, you see a diagram of what the Boltzmann machine looks like, where we have the red visible units and the blue hidden units. So something I want to point out here is on classical machines, we typically implement a restricted version of a Boltzmann machine, where we only include the bipartite connections in the middle. The connections on the extreme left-hand or right-hand side of the figure are typically omitted. So what the Boltzmann machine does exactly is a little bit abstract, so here's a more concrete example. What we've done here is we've trained a Boltzmann machine to model molybdenum sulfide atomic structures. So on the top side of the figure, we see images of atoms in space, and we've removed the top right portion of the image. And we've asked the Boltzmann machine to kind of fill in the blank based on what it sees in the rest of the image. And in the bottom, we see the completion of what's missing, and which the Boltzmann machine is able to do since it models the data and gets an understanding of how everything is supposed to work. So next, we're going to talk about the quantum annealer. The annealer is composed of arrays of interconnected superconducting qubits, which solves a very specific NP-hard optimization problem. It's a Hamiltonian, again, just like the one that we saw in the Boltzmann machine, where it assigns an energy to every possible network state and tries to find the lowest energy state. Now, the annealer is a probabilistic solver. It returns a distribution of results, which is important for sampling and training if we wanted to implement a Boltzmann machine. The important point about the annealer is that it's extremely limited in topology. So ideally, we would want to have a densely connected graph of qubits, where every qubit is connected to every other qubit. Unfortunately, what we're restricted to is what we call a chimera graph, in which every qubit can only be connected to a maximum of 6 other qubits at a time. And qubits are separated into what we call chimera cells. What this means for us in Boltzmann machines is if we wanted to map the Boltzmann machine to the annealer, we can actually only represent a small subset of those Boltzmann machine connections. And here's a picture of the D-Wave, the annealer that we're using. So what do those Boltzmann machine have to do with the annealer? It turns out because they share the same sort of basic problem, that Hamiltonian and finding low energy states, we can implement Boltzmann machines using a quantum annealer. And we can actually use a richer topology than you would usually find on a classical machine. Unfortunately, because of the limitations of the annealer I just discussed, we can only fit small Boltzmann machines onto the annealer. So we could use a process called embedding to fit larger problems of interest, but this is also NP hard, so we want to avoid that if possible. So what we've done is made a modification to Boltzmann machines by using an approximate training method and only representing the hidden units of the Boltzmann machine on the annealer. In this way, we avoid embedding, and it also opens up sort of a playground for us where we can sort of choose which Boltzmann machine subsets, connection subsets, to actually represent on the annealer. So to sort of illustrate the issue here, on the left-hand side, we see the Boltzmann machine's hidden units and the connections between them. And we want to map that onto the qubits of the annealer, the chimera topology we see on the right. So we can't actually fit all the connections there. We can only choose a small subset to represent on the right-hand side. And the choice that we make of which qubits to assign to which Boltzmann machine variables implicitly determines which connections we're carrying with us onto the annealer. So we want to kind of make good use of our limited resources. So one of the observations we make is our choice of how to map Boltzmann machine variables to annealer qubits affects our Boltzmann machine performance, and that this performance impact persists throughout training. So in our experiments, we trained Boltzmann machines on the NIST handwritten digits data. And one particularly, I suppose, poorer performing variable mapping compared to a better performing one, the difference in training time to achieve the same level of performance was around 25%. So the question becomes, given that we want to choose a good subset of Boltzmann machine connections to represent, how do we actually go about doing that? First thought is always brute force. Can we just go through every possibility and choose the good one? If we do a quick counting exercise, it turns out we have exponentially many possibilities. We don't want to do that. So we need to be a little more intelligent. We took the step of using entropy as a guiding metric to kind of choose how to map variables onto qubits. So when we're using entropy, we're looking at entropy within chimera cells. We want to manipulate the entropy either up or down. And from our empirical experiments, it turns out low entropy is good, and that entropy on either extreme, either extremely high or extremely low, should be avoided. And we call this process a dynamic topology reconfiguration because periodically throughout training, we're evaluating our variable mapping choices and reconfiguring it to try to push ourselves towards better assignments. So here's just a quick illustration of what we're doing when we're actually reconfiguring things. So we see here on the left 2 chimera cells with colored Boltzmann machine variables assigned to the qubits. So in one assignment, we could have the blue variables match with red and the green match with yellow. But suppose we want to redo our assignment, and it turns out, we end up pairing our blue variables with yellow and green with red. So we call that qubit swapping. We're just swapping where the variables are actually mapped to on the annealer. So in our entropy approach, we found that using a greedy approach to find low entropy worked best. We developed an alternate greedy method we called the greedier method. It finds even lower entropy than the simple greedy one. While it performs well, we found that it does not perform as well as a simpler method. And sort of in the future work section for us is to implement like a globally minimal entropy assignment. We know how to do this. We've reduced it to the minimum weight matching problem, and it's known to be n-cubed algorithm. So all that remains is just implementation for completion's sake. So we've also performed some validation on our results. We tried training across data sets. So we trained on the NIST data set. We also trained on the molybdenum sulfide data set. Our results held up. And then we also, in the bottom graph, we also trained on the actual D-Wave hardware, because the experiments we did before were on simulator, and our results carry through across both data and hardware. So the main takeaways from this is that we can implement Boltzmann machines on annealers, richer Boltzmann machines on annealers, and potentially give better results. and that the choice of how we map our Boltzmann machine variables to our annealer qubits affects our results. So if we want to make good use of our limited resources, we can use this dynamic topology reconfiguration. And this is something we should keep in mind because limited qubits and limited connectivity is always going to be an issue for annealers going forward. Okay, so questions?
So Scott Miller, I'm in the Boston office. You hear me?
Yes.
So question, it seemed like you were dynamically moving nodes to different qubits as you were training.
Yes.
But if you were doing that, doesn't that change the connectivity of the network? And what happens to all those weights when you change the connectivity?
So when we move qubits around, sometimes we're basically including new connections or excluding ones that we've already trained upon. Nothing happens to them. The weights are still there, but they're just not part of the problem anymore. So we're actually, every time we do that, we're training on a slightly different problem. And we do see slight performance dips whenever that happens, but overall the result is better for us in the long term.
Hi, Alexei, Arlington office. So you mentioned solving the NIST handwritten and digit recognition problem, but also solving some kind of atomic structure estimation. So to me, one is like a classification problem, and the other is some kind of optimization problem. Could you explain why those two very different seemingly problems are solvable by this Boltzmann machine methodology? Thanks.
So for the handwritten digits data, we're not actually doing the classification problem. We're trying to do an encoding problem. We're just taking the image and we're trying to have the Boltzmann machine learn how the digits work. So we're not actually classifying anything. We're just treating it as an image we want to reproduce, similar to the atomic structure problem. If you recall, we had images of atoms in space. We just wanted to make sure the Boltzmann machine could sort of fill in the blank correctly. It's the same sort of thing with the handwritten, the NIST data set.
I'm José Luis Ambite from Annealer, USC. So I may have missed this, but what is the advantage of running it on the quantum annealer? Do you get like faster convergence, or it's just to show that you can do it? You understand the problem?
Yeah. So I mentioned before that Boltzmann machines, when we run it on classical machines, they use a very restricted topology. They only use those bipartite connections. You only have visible units connected to hidden units. You never have any visible units connected to visible or hidden to hidden. So on the annealer, we can do that. We can do that, and because we can use the annealer as a sampler, it can sample from very complex distributions, which implementations on classical machines want to avoid.
Okay, so it would be more efficient to do the structural search on the annealer than in a classical computer.
Yeah.
Is that?
Thank you, Jeremy.